Today we are going to see the need for controller and self-regulating system. Here, in this process, X is the process variable. X is the process variable. It is plotted between time and X, that is the process variable. Here, initially, let us assume that initially set point and PV are together. There is no error. But at T naught, some disturbance is entering into the process. That's why it deviates. It deviates. But the process regulates itself to bring back the process variable to its set point. That is called self-regulating process. Self-regulating process. Here, on the other hand, if you see that here also the process is variable is y. Here also the set point and PV are together initially up to T naught. Up to T naught. At T naught, some disturbance is entering into the process. That's why the process B completely deviates from the process. It doesn't come back. It deviates. Towards it increases. The process variable monotonically increases after the disturbance. The process C monotonically decreases as soon as the disturbance entered into the process. The third one is process A. If any disturbance, because of the disturbance at T naught, it becomes its amplitude oscillatory and it becomes unbounded oscillator. Its magnitude go on increases. Its magnitude go on increases and oscillatory. But all the three cases are unstable process. Unstable. It never returned to its original state. Here, the self-regulating process is like a Tanjore doll. If you keep the Tanjore doll, if you tilt that doll, again it comes to vertical position automatically. Like that, the process for any disturbance, it comes to its original state after some time. That is called the self-regulating process. If a process is self-regulating, then there is no need to have any controller. No need of controller. No need of controller. But on the other hand, if it is unstable, for any disturbance, if it becomes unstable, you need a controller to bring back the process to its stable state. So that is set point, to bring back the process to its stable operating point. Bring back to its operating point. Operating point. This hidden line, dotted line is the operating point. To bring back the process to its operating point, you need a controller. That is the need for controller. This is second case. The third case is this. In this case, it is a CSTR, continuously stirred tank reactor, CSTR. In that CSTR, it is an exothermic process. It is a the feed is entering at a flow rate of F5. That is the raw material entering here. That is a reactant entering the process at a temperature of initial temperature of Ti, inlet temperature of Ti. Its concentration is C suffix AI, inlet concentration. It is exothermic process. The reactant will react here. Because of that, it will generate heat. It will generate heat. I think you know, heat is different from temperature. Heat is energy. Heat is energy. It is in joules or watt second, whatever. Temperature is a gradient of energy. For a fixed amount of mass, if temperature increases, the energy content increases. It is a gradient. In electrical analogous, it's identical to voltage. It is identical to voltage. So it generates heat. It generates heat energy that has to be removed. It is like in a car engine generates heat. It has to be removed. That's why we are having a radiator. The amount of heat generated by the car is removed by the radiator. That's why initially the car is at cold temperature. Initially the car is at cold temperature. After some time, as you ride the car, the temperature gradually increases and it becomes standstill. It means the amount of heat generated by the engine is equal to amount of heat removed by the radiator. Like that, here also the heat generated by this exothermic process has to be removed. For that, there is a jacket. This is the jacket. This is the jacket around the reactor. A coolant, cold water. A coolant is used. A typical coolant is cold water that is entering at the rate of flow rate of Fc. Its inlet temperature is Tci, and it is leaving here. Here it is leaving, but same flow rate Fc, and it takes away the heat. That's why its temperature is increased to Tc naught. As it removes the heat from the process, the process temperature is maintained at T. Maintained at T. That's why the process is leaving the process liquid is leaving the finished product. The product leaving the CSTR at the temperature of T with a flow rate of F with a concentration of Ca. So this is the description of the process. The product is available the bottom. Reactant is entering in the top. Heat is removed by the coolant. A stirrer is used to keep the temperature uniform around the entire CSTR. This is the stirrer. That's all. This is the process. Here, if you operate this process at different temperature, and if you draw the graph for temperature versus amount of heat generated by the process, heat generated per unit time of the process, this is the graph. This is the graph for the process. Sigmoidal graph. For low temperature, its slope is less. The moderate temperature slope is very high. At high temperature, slope is again low. So this is called S-curve or sigmoidal graph. It's a nonlinear. Its behavior is nonlinear. The amount of heat generated depends upon the temperature. Nonlinearly varies. On the other hand, the amount of heat removed by the coolant is following this linear graph, B. Process follows the nonlinear graph A, and the coolant follows the linear graph B. This is plotted between temperature versus amount of heat generated as well as amount of heat removed. One is superimposed on the other. Note that at P1, they are meeting at P1, P2, and P3. They are meeting at P1, P2, and P3. What is the meaning of P1, P2, P3? At P1, amount of heat generated by the process is equal to amount of heat removed by the process. At P2 also, because they are meeting at P2, it means amount of heat generated by the process equal to amount of heat removed by the coolant. At P3 also, amount of heat generated by the process is equal to amount of heat removed by the coolant. All other points, some difference is there. Let us assume that initially the process is at P2. The process is at P2. The temperature of the process is T2. Temperature of the process is T2. The amount of heat generated by the process is Q2. Amount of heat generated by the process is Q2. At this juncture, some disturbance is entering into the process when it is at P2. Because of the disturbance, that is Ti increases. Here, the inlet temperature Ti, inlet temperature Ti increases. That's why the process temperature T increases. As Ti increases, no controller. But they are equal. Here at P2, at that time, some disturbance is entering, that is Ti increases. That's why process will deviate from P2, T2 to T2 dash. The process will come here, T2 dash. Because Ti increases, that's why temperature is increased to T2 dash. At that time, the amount of heat generated by the process is Q2 dash. Q2 dash. But amount of heat removed by the coolant is only Q2 double dash. Q2 double dash. Heat generated by the process is Q2 dash. Q2 dash. Amount of heat removed by the coolant is Q2 double dash. Q2 double dash is lesser than Q2 dash. The heat produced, this is produced, this is removed. Produced is higher than removed. That's why there will be a further increase in temperature. Because less heat only removed, that's why there will be increase in temperature. That goes to T2. Now it goes to T2 double dash. T2 double dash. Q2 double dash. T2 double dash. At that point, amount of heat produced is Q2 double dash. That time, the amount of heat removed by the process, coolant, removed by the coolant is Q2. This is Q2 triple dash. Sorry. Q2 triple dash. This is Q2 4 dash. Amount of heat removed by the coolant is Q2 4 dash. Again, there is a gap, large gap. Because of that, there will be a further increase in temperature. It goes to T2 triple dash. Again, gap. That's why this much gap. Again, gap. Again, gap. That's why go on, the temperature go on increases up to P3. At P3, the temperature of the process becomes T3. That time, the amount of heat produced by the process is Q3. The amount of heat removed by the process coolant also Q3 at T3. That is operating point P3. So, if any disturbance happens at P2, it automatically moves to P3. That's why this P2 is called unstable operating point. Unstable operating point. Because if disturbance comes at P2, that too increase in Ti, it goes to P3. Now let us check what will happen when it reaches P3. Let us assume that there is a further increase in Ti. There is a further increase in Ti. Then what will happen? There will be increase in temperature, that is T3 dash. T3 dash, increase in temperature because there is a further increase in Ti. That time, the amount of heat generated by the process is Q3 dash. That is Q3 dash. Amount of heat removed by the process is produced by the process is Q3 dash. Amount of heat removed by the process is Q3 double dash. Here, Q3 dash is less than Q3 double dash. Produced is lesser, removal is more. That's why the temperature will decrease and come to again P3. It forces the process towards P3, operating point P3. That is called self-regulating. Self-regulating operating point. Operating point. It regulates itself. If any increase, it decreases. What will happen if Ti decreases at that point? There will be a decrease in temperature. That is T3 double dash. T3 double dash. If any temperature decreases, what will happen? The produced heat is higher. Removed heat is lesser. That's why there will be increase in temperature and goes to P3. If it comes to left-hand side, it will be forced to right-hand side. If it goes to the right-hand side, forced to come to left-hand side. That's why this operating point P3 is called self-regulating operating point. It remains at P3. The process regulates itself. We'll check in the other way. That is, initially it is at the operating point P2. The temperature is T2. That time, the amount of heat produced by the process is Q2. That time, there will be a decrease in Ti. There is a decrease in Ti. That's why the process temperature will decrease to T2 double dash. What happens? There is a huge difference in heat generated and removal. Removal is higher. Removal is higher than generated. Removal is higher than the generated. That's why there will be a further decrease in temperature because removal is higher. That's why there will be a further decrease in temperature, decrease in temperature, decrease in temperature, decrease in temperature till it reaches P1. At P1, again, the amount of heat generated is equal to amount of heat produced. That's why it will, for any decrease in inlet temperature, its temperature will fall and automatically it comes to P1 and remains at P1. Here, P1 also a self-regulating point. Self-regulating operating point. Operating point. What happens here? If let us assume that at P1, there will be slight further decrease in temperature, inlet temperature. There will be a decrease in temperature. But what happens? The amount of heat produced is higher, but the amount of heat removal is lesser for any decrease in Ti. That's why the temperature will increase and go to P1. On the other hand, if any increase in Ti, the temperature of the process becomes T1 dash. Here you notice that amount of heat removal is higher, generated heat is less. That's why its temperature will decrease and come to P1. If it moves to the right, it is forced to the left side. If it goes to the left, it will force to right. Anyhow, therefore, the P1 is the self-regulating operating point. So we can say this way. If we try to operate at P2, for any disturbance entered into the process will either go to P3 or go to P1, depends upon the disturbance entered into the process. It never stay at P2. That's why P2 is the unstable operating point. But If you operate at P1 or P3, there is no need of controller because it is self-regulating process. But if you operate at P1, it's at less temperature. That's why the production yield will be very less. Production yield will be very less. That's why it is not economical. If you operate at P3, it is at higher temperature. That's why it is not safe. It is not safe, as well as the product quality is not good. Product quality is not good. That's why we cannot either operate at P1 or this is economically not feasible. This is quality wise not feasible. But if you operate at P2, its quality, quantity, both are good. That's why we have to operate at P2. But if any disturbance enters, either it will drives to P2, P1 or P3. P2 drives to P1 or P3. That's why we need a controller. We need a controller to keep the process variable at T2. That's why a controller is required. Here, initially that process is at T2. At T1, some disturbance is entering into the process, that is TA increases. That's why the process deviates from T2 and settle at T3. Because T3 is the self-regulating operating point. On the other hand, if you operate at T2, if any disturbance entered into the process, that is TA decreases at T1, the temperature decreases, finally it will settles at T1. Since T1 is the self-regulating operating point. If any disturbance happens at T2, either it will go to T3 or it will go to T1. But if you operate at T3, if temperature increases, any increase in temperature, the process itself forces the process to its nominal operating point T3. That's why it come back. Any deviation force the process to come back to T3. That's why T3 is called self-regulating process. Similarly, T1 also a self-regulating process. If you want to operate other than T1 and T3, we need a controller. Need a controller that will force the process to keep at T2. Another example for self-regulating process. Self-regulating process. Consider a level process without any controller. The inflow rate is Qi, so many liters per hour. The outflow rate is so many liters per hour. The level in the tank is H. Suppose there is a sudden increase in inflow rate. What will happen? The level will increase. But Q naught is function of H. Q naught equal to B times root H. Square root of H is proportional to Q naught, or Q naught equal to constant times, that is B square root H. Therefore, if H increases, Q naught also will increase. If QA increases, H will increase. In turn, Q naught will increase. As Q naught increases, its outflow rate, its level will decrease. Q naught increases because of level increases, and it is equal to Qi. Q naught becomes equal to Qi, and then the level becomes constant. So what is happening here? If inflow rate increases, the process raises its level from present level to higher level, so that inflow rate equal to outflow rate. So it is also an example for self-regulating process. Self-regulating process. The self-regulating process here can be used to damp out any sudden changes in the inflow rate Qi. Any sudden changes in the inflow rate Qi. If there is any sudden change in the inflow rate, if it is directly given to the next process, suppose next unit is here, unit 2 is here, unit 1 is here, unit 1 is here, unit 1 gives QI, that has to be given to the unit 2. But if you directly connect, a sudden change in the flow rate of QI will affect the quality of Q2. If you put a level process in between these two, here a step change. But what happens in the outflow rate? The level has to rise, then the flow rate has to increase. It gradually increases. That's why the unitive can handle such changes. There is no abrupt change in the input to the unit 2. Gradual change only. That's why the self-regulating process can be used to damp out any sudden changes in the input.